Okay, so how is everyone today? Good? All right. So we're talking about sequences. So, this is section 11.1, name sequences. And, just the barest definitions here is that fancy N. That style of writing it in is called blackboard bold. This equal to 0, 1, 2, 3, ... So that's called the set of natural numbers. So is the natural numbers. Two, sometimes it's convenient to write that in superscript star there is this set, the set where you start at 1 instead. Is the positive naturals. Three, a sequence is a function with signature naturals to reals, meaning that unlike your previous experience, like with, say, sine's a nice function there, it's the signature of sine is reals to reals. You put a real in, and a real comes out. But a sequence is a function where it's not permitted that you should plug in any real whatsoever. Rather, you're only permitted to plug in the naturals. Okay, so you can plug in 5, but not 5.1. That kind of thing. A few words here, vocabulary words that we need to be familiar with. What's the distinction between the word positive and the phrase non-negative? Right. One is a permissive of 0 and the other isn't. So if you say that x is positive, algebraically you could say this, whereas if you say x is non-negative, algebraically, what do you say? Greater or equal to 0, right? Okay, similar for negative and non-positive, right? So negative means less than 0, non-positive means less or equal. Okay, and then from differential calculus, you learned about functions that they can be increasing, right? So an example of an increasing function would be something like, say, exponential of x. It's increasing. So what's the difference between increasing and non-decreasing?
Non-decreasing could be flat.
Yeah, it could be constant. So like a constant function, like say f of x is 2,414. It's always outputs that same number, 2414. It's horizontal. So that constant function is not increasing. Okay, but it is non-decreasing. Okay, so you could say f from reals to reals is increasing. What that means is that is that if you have A is less than B, and in some sense you're saying I'm going to move from A to B, so that will imply that f of A is less than f of B. So using slightly different symbols, if we write that delta x, the change in the input, is B minus A, because you're moving from A to B. And if we write the change in the output will be what? Right. F of B minus f of A. So writing that, increasing says that a positive change in the input implies a positive change in the output. That's what increasing means. Every time you move right, you know, in the standard picture, the standard axes, every time you move right, you move up. Right implies up. That's what that's saying. So decreasing is similar, except that now instead of right implies up, what is it? Right implies down. It's always right. You're always going to the right. So increasing is right means up. That's increasing. Decreasing is right means down. That's decreasing. Okay. So then what is then what is the difference between increasing and non-decreasing algebraically? So this is increasing. What's non-decreasing? Yeah, it's that one becomes or equal. Okay. So 7. F from reals to reals is non-decreasing. Is saying that if you move to the right, that means that you might have gone up, or you might have not gone up. That'd be fine too. But you couldn't have gone down. Okay, and then writing it in terms of inputs and outputs, you could say it like this: is that a positive change in the input implies a non-negative change in the output. Similarly, you can remember what decreasing means, okay, and non-increasing. So to give you a picture, so like an increasing function, just a brief sketch of something would be something like that. So that's like an increasing function. Every time you choose any 2 points, every time you move to the right, you end up moving up. A non-decreasing function could be something like this. So now it's that some of the time when you move to the right, you don't go up, and some of the time when you move to the right, you do go up. But notice that it's impossible to move to the right and go down. So this is increasing and non-decreasing. And then you can switch the inequalities and flip the pictures upside down to find decreasing and non-increasing. Good. Any question about these things? Okay. So now those are about functions f. Those are about functions f. But sequences are special, so they have their own special name for some of those things. And that is so I could say let A sub n be a sequence. And remember, all that means, it means a function that you input a natural and out comes a real. And instead of using the f open parentheses x close parentheses notation that's usual for functions with signature reals to reals, rather the input is this subscript. Okay, so then 1. you could say that an is monotone. Monotone increasing. So that's a phrase you need to know. Monotone increasing. What that means algebraically is that you take one term in the sequence, say AK. So that could be like A5, and then what's the name for the next one? AK plus 1, and you take the next one. Okay, so then we have two sequential terms there. And to be increasing, it means that the next one needs to be bigger. But the word monotone means this. It means, in fact, this. All right. So it's greater or equal. So like a constant function, a constant sequence, a sequence where every term is, say, pi. That is a monotone increasing sequence. What does monotone decreasing mean? Yeah, this is that same thing, but now you turn it the other way. And then sometimes, algebraically, you want it to not be the or equal thingy. Okay, you just want to be just less than. In that case, the language for that is strictly monotone. Increasing. And now you take a term in the sequence. So just to make sure we don't get too attached to any letters here, I'll say that this one is M. So what's the next one? What's its name? AM plus 1. And notice that that plus 1 is with the M and with the K. It's not the term AM and then you add 1. It's not that. Okay, so now strictly monotone increasing. So you go to the next one and it's got to be strictly bigger. Okay, so then you can imagine for yourself what monotone decreasing and strictly monotone decreasing mean. Any question about that? Okay, good. So here's an example sequence. We could consider something like this. A n is -1 to n. All right. So then would you please evaluate the following? So A0 is whatever it is, A1, A2, A3. So what are those? So A0 is 1, and then -1, and then 1, and then -1. Okay. So I suspect you can probably imagine what continues to happen, right? It alternates between 1 and -1. So this kind of sequence is called, because it alternates its sign, its SIGN, between terms, between consecutive terms. This sequence is said to be alternating, and this particular thing, -1 to n, is called an alternator. So that's what it does. It causes the sign to change. If you were to plot this sequence, so notably, a sequence is a function, and what is its domain? It's domain. Just the naturals, right? So it's only defined on the naturals. So when you draw it, it's not going to be a curve. Okay, it's going to be discrete points. So it goes from 1 to -1. So if this is if that's height 1 there, and this is height -1, then that means I need a definition there, and there, and there. These are not the values. Rather, these are the only places where it's defined. Okay, and then in red I'll plot the sequence. It is 1, and then -1, and then 1, and then -1, and then 1, and then -1, etc. Right? So that's what it does. Just keeps going. But notably, it's discrete points. It's not a curve. Similarly, I could say, what if Bn is 1 over n? But in this case, what's the domain going to be? Can the domain be the naturals? It has to be the positive naturals, right? Has to be the positive naturals. Why does it have to? Why can't it not be the naturals? Can't divide by 0. Okay, so I could ask, for you to evaluate. It's not very. So B1. So B1 is what is it, and B2 and B3. So what are those? 1, half, third. Okay, so pretty straightforward to understand. And then if we plot that, then the first place where there will be anything is at 1, right? There's nothing at 0. Okay, so then it would be like if that's 1, then this would be a half, and that'd be about a third, and the next one would be a fourth, etc. Right? Keeps going. Any question about that one? So of course I'm omitting infinitely many points, right? Okay. What if we take that alternator and that 1 over n? By the way, so this thing, just writing that down, this is called an alternator. And this sequence, in fact, is so common and so important that it has a name. Does anyone happen to know the name of this sequence? Starts with H. And ends with harmonic. Is the harmonic sequence, right? It's the harmonic sequence. Okay. What if, continuing that example, what if yeah, what if we say that Cn is the alternator over n, like that, and you can interpret that as being sort of the alternator multiplied by the harmonic sequence. What do you suppose the name of this sequence is? The alternating harmonic sequence. Yeah. Okay. Good. Okay. So again, I could say, would you please evaluate? By the way, for this thing, what's going to be its domain? Right, the positive naturals. Because again, we can't divide by 0. So I could say, well, could you evaluate C1, C2, C3, C4. So what's C1? -1. And what's C2? Right, positive half. And then C3, negative a third. And then C4, positive a fourth. So notice that it's basically the harmonic sequence, but we just sort of said, I'm going to negate every other term. Okay, so then if we were to plot it, we were to plot it, then, well, you can get a really, actually pretty good idea of what it will look like by doing the following. So, you know, we know all this stuff about functions, right? Like functions f with signature reals to reals. We know all kinds of stuff about that, right? So then, you know, let's not throw it out. You know, let's remember it. So, you know, f of x is 1 over x. If you look at its plot, that's a plot that you're supposed to know. Its name is, you know, is hyperbola. That's its name. So I'm going to plot f of x is 1 over x. I'm going to plot y as 1 over x. And also, I'm going to plot y is negative 1 over x. I'm going to plot 1 over x and negative 1 over x. Okay, so if I do that, then you know, 1 over x will look like this. That's the plot of, you know, y is 1 over x. And then I can plot negative 1 over x. And that's useful. That's useful information, because what's going to happen is that we're going to plot the alternating harmonic sequence. Okay, and basically what's going to happen is that we're going to alternate between the positive one and the negative one, right? We're just over and over again. So we're going to plot. You know, I'll say that, you know, that this is like, you know, 1, 2, 3, 4, 5, 6, 7. You know, so supposing that I you know, correctly and faithfully plotted 1 over x and negative 1 over x, then the alternating harmonic sequence would look like this. It would be the negative 1, and then the positive 1, and then the negative 1, and then the positive 1, and then the negative 1, and then the positive 1, and the negative 1, etc. Right? So the actual sequence is just the red points. All the rest of that stuff is there just to help us understand it. Any question about that? Okay, good. So you know, taking that in mind, what that's telling you is that hey, if you know a function, you know, if you knew something about a function, and the sequence is what I mean is a function from reals to reals, and a sequence is somehow related to it in this kind of way, then you can say some things. So specifically, the kind of thing that we're looking for now is this definition. Limit of a sequence. Let an be a sequence. The limit of an is, in the first place, written this way, so lim, and then now here's the thing, with functions, with like f with signature reals to reals, you can say, well, what's the limit as we go to 3, and what's the limit as we go to, you know, 8, but only from the right. You can say that for functions of that signature, but what's the signature of a sequence? Naturals to reals. And as a result, because when you look at the points of a sequence, they don't cluster together, right? They're all discrete. Like here's that one, all by its lonesome, and then here's this other one, all by its lonesome. You know, they're all isolated. As a result, it only makes sense to calculate the limit of a sequence at one place. And what's that place? At infinity. That's the only place where it makes sense to ask. So the limit of a sequence is, in the first place denoted, lim, n goes to infinity, of an. Okay, and you say that it's equal to L. So this is assuming it exists, right? Because the limit need not exist. And that means what that means, to say that the limit is is L. So let's consider. How about the harmonic sequence? The input is 1, output is 1, input is 2, output is half, input is 3, output is a third. So if you were to trace, if you were to keep drawing all those red points, eventually what would the output get arbitrarily close to? 0. Okay? So what you would say for this particular example, you'd say that the limit as n goes to infinity is 0. Because in the end, the outputs get as close to 0 as you care to name. Okay, so you could say, well, do they get within a centimeter? Yes, they do. Do they get within a millimeter? Yeah. Do they get within an angstrom? An angstrom is about the size of a hydrogen atom. Does it get that close? Yes. Right. Whatever closeness you care to name, we can get that close. So that means for all. Do you know this one? For all, epsilon greater than 0, there exists, do we know this one? I'm getting some yeses and nos. So I'll come back to that, well, I'll do it right now. This symbol is read out loud for all. So for all epsilon greater than 0, and then that symbol, which is more or less just like an E but written backwards. For all epsilon greater than 0, there exists m greater than 0, such that there's a symbol that means such that, but I'm trying to have mercy on you. So I'm just going to write such that. Such that n more than m implies the difference between an and L is less than epsilon. So understand what that means. If you want to say that the limit of a sequence is, say, like 7, then that means that no matter how close you say that you want it to be, we can go far enough to the right on that sequence, and it will eventually be that close to 7. So you could say, we could be looking at this this picture here, and I could say, well, I claim that the limit is 7, and then you say, really, does it get within a centimeter of 7? And I say, well, if actually you go about 4 miles that way, then from that point on, you're always within a centimeter of 7. And then you say, wow, that's incredible. Does it ever get within an angstrom of 7? Well, it does, but now instead of going 4 miles, you actually have to go 400 miles. But I promise you that once you get there, once you go 400 miles to the right, the sequence might still be jumping around, but it never gets more than an angstrom from 7. That's what this definition is saying. It's saying that can we get it to be within epsilon? And the answer is yeah. If you go really far to the right. That's what that's saying. As an aside, those symbols, for all, and there exists, in basically all the math things, like the definition of limit that you learned originally in continuity and things like that, it said that, right? Except it was for all epsilon, there is a delta, whatever. So if you ever find yourself at a math conference, and maybe it's like in, I don't know, some place where you don't speak that language, then you'll still be okay because you can write this and everyone will laugh. Because it's a statement about math theorems and definitions. And it's saying that, just like this definition and the definition of continuity and things like that, it's saying that for every one of these, there is one of those. Right? I can't even tell you how funny that is. All right. So this picture here, again, what it's saying is that if you draw the sequence, and the claim is that the output gets arbitrarily close to L. So we want to get, we want to get that close. And then the way the definition works, it's an adversarial definition. There's two people. It's I'm making a claim. I'm saying that we can get as close as you want to L. And then you say, well, I can think of some pretty small numbers. Does it get within, half an angstrom? So now I'll draw that. Okay, I'll draw L, and then I'll go up your challenging small amount. So L plus epsilon, and I'll draw that. So that's the max. That's the biggest. I'm supposed to find a place where that's the biggest that the sequence ever is from some point on. And then what's the smallest it's allowed to be? L minus epsilon. And so, here's the deal: is that I take all these inputs here. So it's defined on the naturals. Okay. So now the sequence is allowed to be wild at first, right? It could be like, okay, well, it happens to be in that band. But then, to the next one it says, nah, I'm gonna be crazy up here, and then, maybe back in the band again, and maybe I go, back up, and back in the band, and maybe below the band too. It's all over the place. It can be doing anything whatsoever. Okay, all over the place. But here's the deal. What I'm saying is that we can ignore the sequence's behavior when it was young, right? for the indiscretions of youth, right? Just okay, well, all is forgiven. But right here, I'm able to produce an M. I'm able to produce an M, and it will be the case that beyond that M, we never leave the band. It never goes further than epsilon. So, even on that M, according to the definition, it could be outside. But from now on, I can never get further away. And what the definition is saying, is that you have control over this horizontal strip. You have control over that one. And I can always respond by giving you this M, even if I have to go way farther right. Okay, good. So that's interesting. And y'all computed limits before, but with functions of a real variable, not of a natural variable. But here's the thing, is that everything you knew about those functions has to be just as true here, in the following kind of sense. I could say, let an be a sequence and suppose that F with a signature that's from the good old days. Suppose we've got a function that's got that signature. Suppose that is such that in fact an is f of n for all n. Meaning that the function is like a curve. It can be doing any old thing, but it's in agreement with the sequence at every natural input. Okay, so suppose that's the case. Then the limit as x goes to infinity of f of x equal to L. Suppose that statement is true, that you can compute the limit of that function, and you get L. Then what does that mean about the limit of the sequence? It must also be L. Okay. Interesting. So any question about that? So, here's something, what do I want to say? Curious. So here's a function. So for example, f of x, let f of x be sine of x over x. So sine of x divided by x. Okay, and by the way, sine of x divided by x is so important that it has a name. What's its name? Does anyone know it? It's kind of not very common at this level, but if you're an engineer, you should know it. Not yet? All right. Well, as an aside, sine of x over x has a name, and its name is sinc, S-I-N-C, of x. It's quite important in electrical engineering and other engineering disciplines, but sort of notably in that one. All right, so then if we plot sine of x over x, so I'm not really asking you to plot it, rather I'm just going to plot it for you. So what's the domain of this function? Anything but 0, right? Because we're reckoning this to be a reals-to-reals function. So everything is permitted except 0. Now, sine, if you plot sine, it goes through the origin, right? Also, if you plot x, it goes through the origin, right? And as it turns out, sine of x and just x itself, they go through the origin. They both go through the origin, and they go through the origin in such a similar way that, in fact, the limit at the origin at 0 is going to be 1. So that's 1 there. And then from here, it's a wave. It's wavy because sine is wavy, right? But what's the biggest that sine can ever be? 1. And what's the smallest that sine can ever be? -1. So what's going to happen is that it's going to be wavy from here, but it's going to diminish. It's going to diminish. So specifically, if I plot 1 over x, and I also plot -1 over x. So if I plot 1 over x, and -1 over x, then I can't ever exceed. I can't ever get outside of those, right? Because the biggest sign can be as 1, and the smallest sign can be as -1. So the biggest for any x that could ever be is 1 over x, and the smallest it could ever conceivably be is -1 over x. So as a result, this function looks like this. That kind of thing, and it does a symmetric thing going the other way. So that's like a big bump, so it's like, I'll just dot it going that way. So it's symmetric going that way. So it's called sinc. All right. Now, in this class, I forget, do we know L'Hopital's? We do? Okay, so then, recall, or calculate. Oh, we don't even need L'Hopital, do we? Let's just calculate the limit as x goes to infinity of this thing. So you should have a pretty good idea of it from the picture. From the picture, what surely must be the limit? 0, right? So, and in this class, do we know the squeeze theorem for these? Do you know that name? Squeeze theorem? Okay, good. So we want to calculate this. And observe, we want to calculate this, I could say observe that because it's the case that -1 is less or equal to sine of x is less or equal to 1, which is just to say that sine of x is bounded in that way. Because that's the case, that also means that negative 1 over x must be less or equal to sine of x over x, which must be less or equal to 1 over x. So because sine is between the 1's, sine of x over x is between the 1 over x's. So now we can compute limit of every position. So the limit as x goes to infinity of -1 over x must be less or equal to the limit as x goes to infinity of sine of x over x must be less or equal to the limit as x goes to infinity of 1 over x. But what's the limit on the left? What's that limit? 0, right? Sort of like obviously, right? Which is to say that if you take a -1 and you divide it by an x, and that x is getting infinitely big, then where's -1 over x going? It's going to 0. So as a result, this is 0. It's saying that 0 is less or equal to the limit as x goes to infinity of sine x over x, which in turn is less or equal to, so what's that limit? 0. So concerning that sinc function, what we're saying is that its limit at infinity on the one hand must be greater than or equal to 0, and on the other hand must be less or equal to 0. So what can we say? So it's got to be 0. Therefore, the limit as x goes to infinity of sine of x over x is 0. So that's a cute walk down memory lane, I guess. But so I could say that that's question 1. And now I'm going to ask the question that I really wanted to ask, and you tell me what the relationship is. So suppose that I define. I could say let I don't know, let yn be the sequence sine of n over n. So those are like weird values, right? Because because n is a natural number, I'd be asking about like what's the sine of 13 over 13? I don't know, but I don't know what the sine of 13 is, right? That's not a special angle. And 13 is reckoned in radians. I have no idea. But the question is what is the limit? The limit as n goes to infinity of that. So what is it?
0.
It's 0. Why is it 0? Because that function does it. Every one of the points on this sequence is a point on that red plot. Every one of them. Which is to say that if this red plot there is the graph of the function, then the sequence is something like this. It's something like that point, 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 etc. So if you've established that the red is going to 0 and the greens are with the reds, then where's the green going? It's going to 0. All right. So the general idea here is the following: is that so this is called the squeeze theorem for sequences. is we could say let AN, BN, CN be sequences. So we've got three different sequences. And suppose that for little n more than big M, you know, for some big M, it is the case that AN is less or equal to BN is less or equal to CN. And suppose that the limit as n goes to infinity of AN is L, and the limit as n goes to infinity of Cn is L. So, meaning that the limit of the A sequence exists and it is L, the limit of the C sequence exists and it is L. So they both exist, and they're both the same. And furthermore, at first, A's, B's, and C's they can be doing any old wild thing. They can be in any order that you like, right? Maybe A is the biggest one for a long time, and you know, maybe some of the time you know, B is the smallest. But eventually there comes a point where they remain in this order. So if there eventually comes a point where they remain in this order, and furthermore, the left side has a limit, which is L, and the right side has a limit, which is L, then that means that the middle must have a limit, and furthermore, it must be L. So what it's saying, then this, the limit as n goes to infinity of Bn is L. That means that it must exist, and furthermore, it must be L. So as a picture, what it's saying is that, you know, here's L. Here's the inputs. Okay, and there's an M somewhere, right here. Okay, so I'll color these in red, green, and blue. So what this is saying is that you know, up to M, the points can be in any order. So maybe it's like you know, red is way high for that input, and then green is just below it, and then blue is like way down here. Okay, and then you know, maybe now red is saying, nah, you know, I was way up there for a little bit, but now I'm going to be down here. You know, like this. So you can sit here and play this game. Okay, so maybe, you know, red, 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 green, 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 blue, blue, blue. So the red, green, and blue sequences can be doing anything for a while. In fact, they need to do. They can also do anything right there on that one. So they can be doing anything. They can be in any order. But from now on, two things must occur. Now that I've passed M, one thing that must occur is that going from bottom to top, they have to be in the order red, then green, then blue. That has to be the case. Furthermore, red has to be getting close to L in its height, and blue must also be getting close to L in its height. So, you know, from now on, it's going to be like this. So, red, you know, something like this. And then, oops, green, blue. So from now on, they're going to be in that order, red, green, blue. And in some sense, what's happening, you can imagine that the green thing, the blue ones are pushing toward L, and the red ones are pushing toward L. And green has no choice but to be between them, so green is also going to L. All right. So, good. Any question about that? I hear rustling. Are we running out of time? Oh, we're out of time. All right. So that's all for today. Have a nice Wednesday.